Well, today's class is on the Fresnel equations, and I didn't realize it at the time, but this is heavy theoretical physics continuation of what we did last week. Some marvelous work of Fresnel, the artist of physics and mathematics. Beautiful stuff. And I don't want to tell you the surprises in advance. There are many surprises that are going to come your way as we do this. Let's review quickly what we did earlier. We looked at the gravitational law of Newton and the Coulomb's law, and they were very, very similar. And then we said that if you take the Coulomb's law for granted as a given and then use special relativity, you can understand why there's a magnetic force, because when you have a charge that's at rest, looking at a wire, the wire is neutral, so there's nothing's going to happen. But if there's current in the wire, still neutral, nothing's going to happen. But if you start to move, you see those electrons going the other way at a greater velocity as you would see the positive charges that are at rest in the metal. So because of the Lorentz contraction, it looks like there's more negative charge on that wire, and then you get attracted to it. So that's the magnetic force law. And then we show that you could get the rest of the Maxwell equations pretty much by doing theoretical analysis. So just taking Coulomb's law and Einstein's special relativity, wow, you get the laws of electricity and magnetism. Well, almost, all right? If for a moment we take a real broad look at physics, that many years ago in the 1600s, well, from 1500s, 1600s, scientists start to understand that the celestial forces that Kepler studied and the terrestrial forces that Galileo studied are one and the same. Newton's law of universal gravitation, as he called it. It's a unified force theory. Then when we have 200 years later electricity and magnetism in the 1800s, we have the electric force and the magnetic force, and those two were shown to be intimately connected in the laws of electromagnetic theory, the Maxwell equations. So you have gravitation and you have electromagnetic theory. Now, at this time, when Einstein comes along in the late 1800s and early 20th century, there are no nuclear forces yet, so there's only two basic forces in nature, gravity and the electromagnetic force. And Einstein wanted to unite those two. And that's the idea of the unified field theory, which string theory is trying to do today with the additional two nuclear forces, the strong and the weak force. But if you look at special relativity and Coulomb's law, you can get the Maxwell equations, like almost, from the theory, basically that, we did it in the other class. But then when special relativity gets generalized to general relativity, you have the modern theory of gravitation, where you can derive Newton's law of gravity as an approximation of the true law of gravity from general relativity, which means special relativity and general relativity. If you have relativity and Coulomb's law, you got it all right, except for nuclear physics. And you say, what about chemistry? PV is nRT. Oh, you get that too, because if you have, we do have to add F equals MA, and we have to add the force is Q times E vector plus then Q V cross B. So you have to have the force equation, Lorentz force, and Newton's second law. So with that, you can then derive PV as nRT by collisions of molecules reflect and change momentum against the walls. So really you can develop thermodynamics. There's a way to define temperature in terms of the agitation, the molecular, the motion. So you can pretty much see all of physics in this nice way. Okay, so let's get on with Fresnel. Chapter N, the Fresnel equations. And 0, theoretical physics continues. Part 3. Today, we cover Fresnel, the main scientist, civil engineer and physicist, and an extraordinary theoretical physicist, as you will see the beauty of his work involving light. Let's take a moment to reflect. We've covered a week of theoretical physics last week, and let's reflect on the philosophy of the derivation and address the question, why derive everything? Here is Feynman's blackboard when he died. It says, what I cannot create, I do not understand. So if you can't work it out, you really don't understand it. So this is a very, very good goal in physics, to work things out. Here, know how to solve every problem that has been solved. So we're taking this approach in our class where we look at things, we are deriving everything, showing all the steps, working things out for ourselves. You're doing that for homework also. So if Feynman couldn't derive it, he felt he did not understand it. And this is a great goal. So we continue today with our derivations. And the first thing we're going to look at is N1, the plane wave model. Now this model is a very nice one with waves that we already looked at. If we have Y and we have Z and we have X, this is our coordinate frame that we looked at. Here's the electric field along X, and we have the magnetic field along Y, and the wave's going to travel down the Z axis. So we can write E sub X as E naught sine of KZ minus omega T. And By, so a quick little review here of what we've done so far with light waves, Kz minus omega T. And the connecting equation, E naught over B naught, is C, which is omega over K. And remember C, 1 over the square root, epsilon naught, mu naught. So we can write this in vector form. We can write down the vector E is the EX I hat, so that the EX would be here, the magnitude, and that's changing. This is actually the maximum, the E naught here. And then B would be a BY J hat. Notice that I cross J is equal to K. These are your unit vectors. If you look at the I, that goes along the x-axis, and if you turn I into J, which is this way, like with the screwdriver, then you advance along Z. We're using I here a lot, by the way. We're going to be doing a lot of duplication with letters. I can be the square root of -1. I can be the unit vector. I can be the current, all right? And I can also be the incident, the angle, coming in, the incident ray. So here, we're going to write in general, if we can write down like you do in math class, the R vectors, xi hat plus yj hat plus zk hat. Since here, this k is going to be along z, we can make this a vector, k with a k hat. So then if we take the k vector dot r, we would get k hat dot, and remember your dot products. If you're perpendicular, it's 0, and if you're parallel, a dot product with the unit vector is going to with something with itself is going to be 1. So if you look at these, k dot I 0, k dot j 0, k dot k 1, and what survives here is kz, which is what you have up in there. So that means we can write for the vector E naught, I'm going to write this one out, sine of k dot r minus omega t. Since the k dot r is the kz, we can write that in a more general case. Since we're looking at this r vector, let's just review a little bit here. This is your k. This is the way it's often set up in math and physics classes, where you have k pointing up. So let's do that. If we look at this case where the z is up and the x and y this way, then if you look at a vector to a point P, all right, then let's look at what's going on here. If you drop down here to this plane, then you can make a rectangle in here, so right angles, and you have, then this is your x, this is your y, and this is your z, your height. And then you have your little unit vectors, this would be k hat, this would be j hat, and this would be I hat, and I cross j. We turn I into j from underneath, we're gonna go up to k. So let's look at this in more detail. So if we look at this system where you have this r vector, I'm going to here make a door. This is like a door here, like we're opening up a door. So we have z, we have x, and we have y. And if this is r, then we're going to use the angles used most of the time in physics, and you might see them interchanged in some math classes, but this is the angles that the physicists like to use. So r times the sine of theta is the top of our door. If you take r times the cosine, you get this length here, which is the same as this length here on our door. This is r cosine theta. This is your z. That is z. So that's z. See? And then here, r sine of theta is also the other side of the door, the bottom of the door down in here. That's r sine. And then if you look at, go ahead and choose a different color here. If we look here at this and say that, then you're looking at here, this is your x and this is your y, but see your y here would be this hypotenuse, r sine of theta, times the sine of phi. And then this one here would be the cosine of phi. So you have, this is your hypotenuse, r sine of theta, and then if you go cosine of phi, you get this one. So this is your x, and this is your y, and there's your z. So you have them all. And then you can write in general that the r vector is r sine of theta cosine of phi, I hat, plus r sine of theta sine of phi j hat, plus r cosine of theta k hat. And if you have 90 degrees for your theta, if you bring this theta up to 90 degrees, then you're in the plane, the xy plane, and then this becomes a 1, this becomes a 1, and this becomes a 0, and you have polar coordinates. You're just in this plane here, where this becomes r times 1. This is like the r, and then you have your cosine. Remember, your x is then r cosine of phi. Y is r sine of phi. Polar coordinates. Okay, so to adapt our wave to the general case, we look at this. This is the general case here. And if you consider like some kind of weird, say you have an E and and a B, perpendicular, and you're going to go in some wild, direction, where this is r hat. We're good. We're good to go. we can use this form. This is the general form. And then if we go along to z, then you can you see how that k dot r gets you to kz, which is what we have up there. So that's very, very powerful to use that formula. And we can now look at why that's called a plane wave, the plane wave. Let's do one more thing before we go to the plane wave. Let's go to the exponential form and to generalize this e so that it can be anywhere. I'm going to make it clear by having an e vector times an e to the I k dot r minus omega t. So this is like really general now, really powerful, where we go ahead and if we orient this a different way, this is showing us that you have a more general polarization. Remember, your E fields your polarization. This E is aligned along X, so oscillating that way. We say it's vertically polarized light, or vertical polarization that's along the x-axis. And in general, this is allowing for some combination of two perpendicular components. And that's your more general formula. Now, they call that a plane wave. And I always had trouble with that when I was in undergraduate. Like, what do you mean plane wave? How's that a plane? But here's how you can understand it. If you think of a point source sending out waves in all directions, then these are cute little plane patches. See those cute little plane patches? It's nice. There's another one there. So the wave that's going out, say this is like your direction of the wave, the r hat, then here you can think of the little plane, and you have like an electric field. It's going to be oscillating, say up and down, but you can think of it as a cute little patch. So that's a nice way of looking at it. Here's another example here where they show these little patches and the waves going in that direction. So it's sometimes called the plane wave for that reason, but it's not a big deal. You just stick with the math, you're in good shape. Okay, so here we go on to our next part, and that's N2. And N2, the Maxwell equations in matter. Since we're interested in light going into glass, we need to deal with a more general Maxwell's equations. And here, the way to think of that is that your epsilon naught in a vacuum is going to become an epsilon, and your mu naught is a mu. So the electric and magnetic constants are going to be more general. So if we look at the Maxwell equations, the first one, E dot dA, is Q over, here I put epsilon instead of epsilon naught. And here, because when you have glass and various materials, you can get polarization effects where charges might bunch up a little bit, but they're bound charges. So you make sure that this refers to the free charges. We put free there for emphasis. Then for the magnetic field, no change, no magnetic monopoles. And then if you look at Ampere's law with Maxwell's piece added, we're going to go mu with no naught, take the naught off, and then emphasize that the free charges are the ones we're interested in, the ones that move, the free charges move, and then take the naughts off. And this is the change of the electric flux with respect to time. And then finally the Faraday's law, the last one here, is minus. Now here, we're going to be interested in materials that are non-magnetic, but it's a neat way to look at this epsilon and the mu. You can think of this as an epsilon naught, 1 plus some additional component, and here mu naught, 1 plus some additional component. And this is called the electric susceptibility, and this is the magnetic susceptibility. How does the material respond? And here, if it's a non-magnetic material, this is going to be 0, and we're going to have mu equal mu naught. So So here, we're not going to be worried about charges that are free moving around, conductors and stuff. We're not worried about that. We're going to be looking at like two media, air to glass. So we don't want this one. We're not going to be dealing with this equation. And then here we want no currents. All right, and then this is going to be, this one here needs to be an epsilon without the naught. All right. Then here I can make this though mu naught because it's non-magnetic. So really I got like two equations here. I got this equation, B dot dl is mu naught epsilon d phi dt. I got this one. And I have then the Faraday's law, E dot dl is minus d dt. All right, there's what we got. We got those two. Now remember that the speed of light in vacuum is 1 over the square root epsilon naught mu naught. And now in the material, it's going to be 1 over epsilon without the naught, but the mu naught is still there because it's a non-magnetic material. So if you want to look at the definition of the index of refraction, which by definition is the speed of light in vacuum divided by the speed of light in the material, then this is 1 over the square root, just copying from above, with the naughts, and 1 over the square root epsilon with the mu naught. Here, these are going to cancel, and the epsilon is going to flip to the top, and you're going to get this cool relationship that the index of refraction is epsilon over epsilon naught. And that's important, that the epsilon is not epsilon naught, because then you'd be in vacuum, and then you have no material. So here, this is nice expression that gives us the index of refraction in terms of the permittivity of free space and the permittivity of the material. So we go to N3. Interface boundary conditions. What do the Maxwell equations tell us about boundary conditions? So we're going to look at here, let's look at two materials. This is N1 up here and N2, index of refraction. And we're going to go at two analysis here. We'll have another one over here, N1, N2. So if I have a static electric field, say like points here, this electric field static, and here there's an electric field in the other material, E1, E2. We got E1 and E2. And here we're going to have a magnetic field, static, and that's B1. And here's some other one, some other direction, B2. And what can we say about the boundary? So what we're going to do here is look at, for this one, we're going to look at this equation, E dot dl is minus the magnetic flux, dt. And what I'm going to do is make a loop that's very, very thin. In other words, this is delta, this thickness. And here, the length, we can call that L, the length L. So very, very small thickness, say delta, and then there's L. So here, if you look at going around, like say this is your DL, this is your DL, this is a DL. Since this is so thin, there is no flux. So I'm doing this in pairs here. So the B dot dl is equal to the mu naught epsilon, the flux, electric flux, with respect to time, gone. Because when I bring that really close to that interface, there's no area. And there involves an area in the flux. So this is saying that the E dot dl, so the E2 on this side, and I'm going to say that's the parallel component. When you take the dot product, you're lined up, you got to be lined up with the L to get the contribution. And then if you go the other way, we're against the grain. We're against the E direction. So that would be, this would be times the big L. And there's nothing on the side since that delta is going to be essentially 0. Then minus E1, and that's parallel, L equals 0. So E2 parallel minus E1 parallel, L equals 0. E1 parallel equals E2 parallel. So that's the boundary conditions, that the electric field components that are parallel to the surface on either side must be equal. And, without needing to do the others exact same thing, B1 parallel equals B2 parallel. So they're the boundary conditions at the interface. And they're very, very important. They're going to be our guide in the next section. Okay, so now we move on to N4, which is an E&M wave at an interface. Now for E&M wave at the interface, I'm going to construct here a coordinate system. Let's go here with X, and we'll make this Z, the normal way of doing it. And here we're going to have a wave come in, and you can think of this here as being two materials, say glass and diamond, for example. And then here we're going to bend. In fact, we don't really know what these angles are. Say transmitted and some reflected. So we're setting this problem up. So we're going to send something in from the top and then allow for a reflection and a transmission. Nothing's coming from the bottom. So here you can give a vector for the incident, an incident K, and here is a reflected K, and this could be a K transmitted for the three directions. And for Z greater than 0, above, we'll then have two solutions. We'll have, say, E vector incident sub naught for the polarization, E to the I, K incident dot R minus omega incident T, plus a reflected beam where we have the K reflected dot R minus omega for the reflected times T. Then for Z that's less than 0, that's below the plane, the XY plane, then you just have the transmitted. And that would be transmitted beam sub naught E to the I, K transmitted dot R minus transmitted times T. T's used a lot also here. Okay, so now what we're going to do is set the E parallel on the top side, E parallel on the bottom side, but right at the interface. So this is right at the interface. So if that's the case, that means at the interface, the parallel of this must be the parallel of that. Now this parallel stuff is going to be coming from these vectors, right? Since these are your like sign fluctuations. So for that always to be true, that has to be true for all R and T, see, along the interface. Well, if the T is going to vary, the only way that's going to be true if the omega T's are the same. So that means the omegas have to be the same so that we don't get some weird stuff going on. So that means that the omega for the incident equals the omega reflected equals the omega transmitted. Very, very important conclusion, because this has to be true all the time, and this T is arbitrary. So I can't count on this, happening for just a specific T. It has to happen all the time. So that is a requirement. Now remember what omega is. What is that? Well, I like to remember that the velocity is omega over k. And then I like to remember k is 2 pi over lambda. And then I like to remember the index of refraction definition, c over v. And if you are not sure of this one, watch this trick. This is omega over, this is 2 pi over lambda. The lambda flips. Omega is 2 pi f. These are the friendlier formulas. 2 pi's cancel, and you get the famous result that the frequency times the wavelength is the velocity. So, I mean, this one is most friendly. This is most friendly. This is most friendly, right? This is most friendly in terms of basic physics to remember. So this one, the velocity one, this one, angular frequency, wave number, and this, these are to be remembered. If you can remember this one also, that's good, like the phase velocity, remember omega over k. But if not, you can always get it easily. So for these omegas to be the same, you can think of the omega as a kV. All right, so let's just do that for now, a kV. There's many ways you can approach this. I'm going to just say omega is kV and just substitute. So I have k I VI is k reflected, V reflected is k transmitted, V transmitted. But there's many ways you can play with this, but let's just do this straight substitution. Then the straight substitution for V in terms of the index of refraction, since I like that index of refraction, V is C over N. So this is then going to be C over N I, and there's be a Ki floating around there. And this is Kr, C over Nr, and this is Kt, C over Nt. All right, now the C's are all going to go. And since the K is the 2 pi over lambda, I can write these in like this. And the 2 pi's go. The main thing here is that the lambda incident times the index of refraction in the incident side is equal to the reflected wavelength times the index of refraction of the reflected in the medium. It's the same medium. These are the same. That's going to give us something profound here. And this is the transmitted times the transmitted. So these are the same, N1, and this is N2. So what this is saying is that the wavelength didn't change since the index of refraction is the same. However, when you look at the transmitted one would be the incident case divided by the transmitted. So since you're going to just divide by NT, so divide by NT. So that means this thing's in the numerator, NT's down here. And this is saying the incident wave, this is the incident is N1 over N2. So if you're going from air to glass, air has a less index of refraction of that. So if this is going to be a fraction, then that means the transmitted wavelength is less than the incident wavelength. And we know that from way back when we did the marching soldiers. Here, notice this wavelength, the distance between the rows of the soldiers is lambda I, and then here when they hit the mud, they're a bunch closer together. And that's because of conservation of soldiers. If you're watching them go by, this certain amount have to go by, same amount have to go by per minute or per hour. And so they travel slower here. They have to be closer together so that you don't create or destroy the soldiers. Okay, so this is A. We can call this as like big conclusion A, all right? But now big conclusion B is going to be with the K's because since the R's can be anything, you know, this has to be also true for the K's to make it true always. So in other words, Ki dot R has to equal K, and this is part B to deal with the space. Part A was dealing with time. Now we're dealing with space. R, this is a dot, and then K transmitted dot R. So these have to be the same also. And I'm going to pick an R here, writing out from this origin. There's my R. And that R is going to be along the Y direction. So I'm going to pick R to be R times J hat. Okay, now when you take the dot product here, we're going to take the dot product. Remember dot product, you have two vectors. Let's say I have a K vector coming in here, and I have an R vector. So what you do is you can put the tails together, but you can't stretch or rotate the vectors because that would change them. But you can move it in place like this so that the R is up here. You don't change the vector if you don't stretch it or rotate it. So that's still the vector, and here is the K vector here. And then the angle between them, say alpha, what you want is K R times the cosine of alpha. But what is that angle? Well, if you look at that angle, in fact, if I were to just put a little horizontal here for the R, then my alpha is up in here. But notice that this is complement to theta, theta I. Isn't that cool? So this alpha here, alpha I, we look at the alpha, is going to be pi over 2 minus the theta. And that's going to be true for all of these. It works the same way, all right? Because this is going to be always going to be horizontal. So since you want the cosine of this one, that's the sine of the other one. So this is going to be KR sine of theta. So now I have this cool relationship. The incident, K times R with the sine of the incident, is equal to K reflected, R, times the sine of the reflected, equals KT, R, sine of the transmitted. Now, when we look at this, look at these three, let's go back to what K is. K is 2 pi over lambda. So K is 2 pi over lambda, and the velocity is lambda times F, and N is, I always go to my basic formulas to figure out what I want to do next. And what I would like to do here, the R's are going to go. The R's are going to go. I would like to get rid of that K. I like to get index of refraction things in there. So if I look at this K is 2 pi over lambda. And if I look at this equation, 1 over lambda is F over V. So this would be F over V. This is the angular frequency. And, you may notice that we're back to this. All right, see all these, you can arrive at this different ways. But see, this is telling me that this is going to be omega over V, which you might say, well, you kind of shouldn't have to do that. If you just remember this, you would have had it. Well, okay, that's all right, no big deal. So that means that we have Ki is going to be omega I over Vi. Now that 1 over V, if I go up in there, that 1 over V is N over C. So I'm going to replace the K with omega N over C. And now I have my three equations. I'm going to have my Ki sine of theta I, which is K reflected, sine of theta reflected, which is the K transmitted, sine of theta transmitted. I'm going to replace the K's with omega I Ni over C. And this is omega R NR over C. And this is omega T NT over C. Now, I know that the omegas are the same, and the C is a constant. So now I have a simplification, Ni, sine of Ni, is equal to Nr, sine of theta R, and that's equal to Nt, sine of theta T. Now, since the n's over on the left side are equal, this is N1, this means that the sine of theta I is the sine of theta reflection, and we have derived, whoa, law of reflection. That's amazing. And you've probably looked ahead and know where this is going, because this one is Snell's law. Because see, this is your incident, this is your N1, this is your transmitted, this is your N2. So N1 sine of theta 1 is N2 sine of theta 2. Can you believe that the Maxwell equations derive the law of reflection and the law of refraction? We've derived Snell's law. And this is from basic first principles, so there's a certain elegance to this particular derivation. Amazing. Here's a nice picture. Looks like they're going from air to water here. And you see the red beam refracted and reflected, see, and the green one. Very nice, very nice. These come from the Maxwell equations. And now we come to N6, the core of today's class, the Fresnel equations. Fresnel died young of tuberculosis, and that reminds me of two other artists. I look at these as all artists, the art of physics, the art of poetry, and the art of music. You have here John Keats, 25, dying of tuberculosis. Frédéric Chopin, 39, same age as Fresnel, dying of tuberculosis. Before the time of antibiotics, back in those days, they couldn't cure tuberculosis. Let's take a moment to look at Keats, the ending to his Ode to a Nightingale, where hear a bird in the evening, imagine it a little darker. He hears the bird singing and he's reflecting on life. And the last stanza, forlorn, the very word is like a bell, to toll me back from thee to my soul's self. Adieu, the fancy cannot cheat so well, as she is famed to do, deceiving elf. Adieu, adieu, thy plaintive anthem fades, past the near meadows, over the still stream, up the hillside, and now 'tis buried deep in the next valley glades. Was it a vision or a waking dream? Fled is that music. Do I wake or sleep? As the bird then flies to another meadow over the still stream. And let's take a moment to listen to the end of the Chopin Third Scherzo. we go to look at the art of Fresnel, the art of physics. Keats lived in the Romantic period in literature, Chopin in the Romantic period in music, and Fresnel in the early wave optics period, where scientists were still trying to figure out what light is. So for the Fresnel equations, we're going to look at, okay, here's our situation. We're going to have here incident, and we're going to have here reflected, and we're going to have transmitted. Now I'm going to pick the two general cases you can have, and that's an electric field that is in the plane that's made with the normal. So if you look at this, normal here, and the incident ray, that defines the plane. This plane is the YZ plane. And then for homework, you're going to do the case where the E field is sticking out of the page. This is called a parallel case because you're in the plane, and the other one's called the perpendicular case, and you're going to do that one for homework. It'd be a nice exercise. So here, the B field points out so that when you have E cross B, screwdriver on the other side, you're going to be coming down, or use your right-hand rule. Here, this is your K direction, so your E vector crossed with the B vector here is going to get you in that direction, Ki. And this is theta I, and this is theta R over here. And on this side, we can take, and here, if you pick E point the wrong way, just get a minus sign when you do the work. I'm going to pick the E flipped because when an electric field hits a surface, like a rope, it hits a hard surface, how a crest turns into a trough, it flips. So this has the flipping in there. So I'm going to do this, but other authors may choose differently. And as I say, you just get a minus sign difference if you pick one versus the other. So here is then coming out. Now it's important to check that if you take the E, cross it with the B, you're going to go up, and that's correct. That works. This is the KR. And then here, if I pick E to be like this one here, then everything's going to work fine. That if you take the E, cross the B, point up, again, you're pointing down. So everything's looking good. And this is the angle of transmission. All right. This is N1. This is N2. All right. A lot of books will just call this NI or something, equals NR, reflected. And this is N transmitted, but I like to use 1 and 2, and eventually replace the angles, this angle, with theta 1 and theta 2. The reflected angle is the same. Okay, so let's see what we have here for now. The tangential components come in. See, we haven't used the boundary conditions yet. The tangential component with the tangential components, of this electric field. So that would be E I naught cosine of theta I. So like whatever this magnitude is, if you do it with the cosine of theta, now here's where we go again with that little line. See, if we have this little line in here, I want, for the tangential component, I want, when it gets down here, I want the cosine of this angle. But see, that angle is complementary to this angle, which is complementary to the theta, so that is the theta I. This is actually easier to work with. It's the same angle. So this angle theta I is complementary to this angle, which is complementary to the angle between the direction of the interface, the Y, the horizontal, where I need to do that parallel component. So I have this, now this pointing the other way, so I have a minus sign, and that's the cosine of theta R, which is the same angle. And that's going to equal the transmitted case, cosine theta T. All right. Now for the B's are simple. They're all pointing out of the page. So they're all aligned up. So that means B I naught plus B R naught in the top part equals the B, and these are parallel to the surface. See, they come out of the page as parallel to the interface. So that's the interface here. So you got to be careful that when we say parallel for the boundary conditions, we mean parallel to this interface. So that's why we took the E cosine of the theta I. But for the B, since it is skimming the surface, we're all set. There's nothing to do there. Just put them together like that. Okay, so then it's time to look at these. That this is theta 1 and this is theta 1. And I'm going to go to call this theta 2. So I have cosine of theta 1. I have EI naught minus ER naught, just copying down this equation. And that's equal to ET naught cosine theta 2. And then for the B, nothing changes. Basically, this is the same. I got this pair of equations here to work with. Now, the connecting equation that we had earlier in magnetic fields, and we got this equation. So we need to bring this back into play. That was in the vacuum. And here, we're going to apply it in general. So we'll replace the C with the speed of light in the material. And these speeds are connected by the famous ratio here, index of refraction. I would like to hear everything in terms of E. So what we're going to do is we're going to flip this. In other words, the B naught over the E naught is 1 over V. We're going to flip this. And if you have 1 over V here would be the same as dividing the N by C. So this is N over C. So therefore the B becomes N over C E. So that means this equation, get rid of all those B's. So if we do that, get rid of all those B's, we'll have N1 over C E I naught. And then for the reflected one, since we're in the same medium, it's still the same here. And that's the E reflected. And then for the 1 over on the right, it should be N2 over C. And that would be the E that's transmitted. Okay, now you can see that these C's go away and we get some really neat compact equations here. We have, let's go ahead and write this down again. We have the cosine of theta 1, EI incident minus reflected is E transmitted, cosine theta 2. And then we have this equation here, N1 EI naught. I'll go ahead and put the parentheses there since we're just adding those two together like that, is equal to N2 E T naught. All right, so now we're really interested in the ratio of these with respect to the incident one coming in. So really what I'm interested in is setting this up, the cosine of theta 1. I'm interested in dividing by the incident one. So this is 1 minus the reflected one over the incident one. So I want to compare with the light that's coming in, what's going to get reflected and transmitted. So this is E T naught over E I naught cosine theta 2. And do the same thing here. I'm going to get N1 1 plus ER naught over E. So ER naught over EI naught, and that's equal to N2 and the T naught over there. Okay, so these are the two equations now that we're looking at. by simply dividing these by E sub I O. Now we're going to call this one the reflection coefficient, R, and this one the transmission coefficient, T. Now if we do that, the equations look even nicer. We have 1 minus R for this one, and this is then T times cosine theta 2. And the next equation is N1, 1 plus R is N2 T. I had a friend in grad school that would bracket pairs of equations, like when he's looking at trying to solve two equations, two unknowns, because your two unknowns here are your R and your T, to keep track of the equations, the pair. So we're going to use this second one here to solve for T, just divided by N2, and then take that and put it in here, get rid of it, then solve for R. So if we do that, we'll get cosine of theta 1 on the left side minus R cosine theta 1 on the left side. And that's going to equal then the T, N1 over N2, 1 plus R times the cosine of theta 2. So if we work out this right side, we have N1 over N2 times the cosine of theta 2 plus the N1 over N2 with the R cosine theta 2. Now we were solving for R, so we would like to collect the R on one side of the equation. Let's get this one on the other side. So the cosine of theta 1 minus R cosine theta 1, and then minus N1 over N2 R cosine theta 2 is equal to the one that's left over, N1 over N2 cosine theta 2. And I really would like to have these, I would like to have the R's by itself one side of the equation. So here's what we're going to do. Let's bring the R's to the other side and subtract this. So we'll have cosine theta 1, and there's different ways of doing this, algebraic steps, but I'm going to just get this one over here on the left side with the minus sign, and then bring these over on the other side with the positive. So, maybe I could have done this shorter, but it's okay. It's the process. This is real life, how real folks work things out rather than copying from a book. That's part of the idea of working everything out for yourself. So if you go in circles a little bit, no big deal, you'll find your way out. We're getting our way out here now. And I'm gonna multiply by N2. So N2 cosine theta 1 minus N1 cosine theta 2 is then here N2 R cosine theta 1 plus N1 R cosine theta 2. I'm gonna be finished now. Because see, this R factors out here. This is N2 cosine theta 1 plus N1 cosine theta 2. So then the R will be this left-hand side, N2 cosine theta 1 minus N1 cosine theta 2. And then divide by what you have over here. I'm gonna write the N1 first, N1 cosine theta 2, but that's subjective, you can either way. And that's the equation. Marvelous. Okay, so here's what we have for the coefficient of reflection, and we know this formula for T. So to find the T, we're going to take N1 over N2, 1 plus R, so I'm going to set this up with the common denominator, N1 cosine theta 2 plus N2 cosine theta 1, and put that same thing up in the numerator. So I have a fancy way of writing 1. And then I'm going to add the R to that. And now we just copy down, the denominator is the same. And the numerator, we just copy. So what's going to happen here is that n2 cosine theta 1 appears twice with a plus sign. The n1 cosine theta 2, that one appears with a plus sign and then a minus sign. So that one goes. And then finally, here, I'm going to have 2n2 cosine theta 1 over the n1 cosine theta 2 plus n2 cosine theta 1. One last step is that this factor in the front is going to change the n2 to an n1. So then I'm going to have 2 times n1 cosine theta 1 over n1 cosine theta 2 plus n2 cosine theta 1. And there you have it, the Fresnel equations. And this is for the case where the electric field is, parallel to the YZ plane. So we'll put a P there. You're going to be doing the case where it sticks out. And that's called S for German, the word like perpendicular. So that's going to be for homework, but this is what we have here. And now this really blows me away, because if you take the coefficient of reflection and you square it, you're going to get what's called the reflectivity. Reflectivity then, and that's going to be let's do it. So let's figure this out. If you have air and you have glass, because I remember someone telling me way back that if you shine light at glass, like normal incidence, like 4% comes back. And you get like 96% entering and like 4%, comes back. All right. So here, it's easy to do this because you have N1 is 1, N2 is 1.5, and then the angles, if they're incident, angles all 0. So you get all these to be 1. So here, all these cosines. So this is 1.5 minus 1 over 1 plus 1.5. So this is 0.5 over 2.5, which is 1/5. And then if you square it, you get 1 over 25, and that's 4%. That is amazing. That the Fresnel equations tell me how much percent, what light is reflected. Isn't that incredible? We just don't have the law of reflection and refraction. We got this kind of detail that's coming on here. Just amazing. Notice, by the way, if you do the transmission, try the same trick here, you get into trouble. This would be 2 times 1, and then this would be 1 plus 1.5. So this is 2 over 2.5. And that's equal to 2 over 5 halves. That's equal to 4/5. So if you square that, you get 16 over 25, and that's not equal to 24 over 25, which is what you expect, because if 1/25 reflected, you then should get 24 25ths coming through. So don't panic here. You just trust the mathematics. We trust the mathematics, and the mathematics says that, if you did this, it would be corrected if you multiply this 16 over 25 to get the right answer, which is, this is the correct answer, 24 25ths. You would have to take the 16 over 25 and multiply by 24 over 16. Now see, we're discovering something here. So this reduces the 3. You can reduce this. 8 goes into 24 3 times, 8 goes into 16 2. So what's with this 3 has? Well, see, 3 has, that is the index of refraction of glass. So what the mathematics is teaching me, that yes, you did the intensity, you squared like the amplitude up there in the air, but it's saying for the glass, you really need to have the n in front. See, so that's what this is showing. This is showing me that in general, you need to bring in the index of refraction. That is wild. So that's some deep physics, and the mathematics is teaching me that because, naively I tried to just do the same thing with this. Now I do know that the t has to be 1 minus r for conservation. So I do know that if I subtract the 1 over 25, I need to get 24 over 25. So I am confident that this is correct. But when I use the t squared thing and get the wrong answer, I see that I need to correct for it, and that leads me to this conclusion. Okay, we're basically finished our class, and I just want to summarize here that we have done the polarization case on the left. You're doing the polarization case on the right for homework. And just one last step, if you want to show off complicated formulas, maybe we should just do this one last thing to just show off a little bit, that if you have, you have this r that we figured out today, n2 cosine theta 1 minus n1 cosine theta 2 over n1 cosine theta 2. Suppose you want to get this elegantly in terms of theta 1. You want to get rid of theta 2. Well, you know the Snell's law, n1 times the sine of theta 1 is n2 times the sine of theta 2. So I know that my sine of theta 2 is n1 over n2 times the sine of theta 1. And I know my cosine of theta 2 is the square root of 1 minus sine squared. So I can then write the cosine of theta 2 as 1 minus n1 squared over n2 squared sine. So now if we want to show off, we can take this and stick it here, and we can take it and stick it there. We get a really complicated looking formula. So that's the formula here. If you do that, you get something crazy like this. And that's the formula you show your friends. Okay, so you're going to be doing this other case for homework, and look at this marvelous plot. If you look at the case that we did here the parallel case. I did this red one, this dotted red one. And you're going to be doing the S case, all right, which is the other polarization. That's called S because in German, that's the German word, correct. Yeah, correct. That means perpendicular in German. Some books will just do T parallel and T perpendicular like this. We'll use the S and the P notation. So this is the one that we did here, the RP and the TP. We did this. And then here, next class, we're going to do this surprise, like what is this? In other words, the reflection of this polarization is like 0. Like, what is that? Now, the other polarization you're doing for homework is not 0, but the one I did will be 0. We'll look at that next class. Probably can't resist doing one last thing, that if you look at the normal incidence here, you get this cool formula where, say, the theta 1 is equal to 0. You get n2 minus n1, which we already looked at with the glass, but I just want to emphasize it again. So that means the reflectivity would be, you have the difference, you have the sum, and you square it. That's cool. And then for the t, you just subtract like that. So that's neat. This is a normal incidence, which is in general what we did for the glass. Okay, very good.